Hello physics students. So in the last video, you learned this incredible theory called quantum mechanics. And the essence of what quantum mechanics says is that the worldview of what the world is and how it works, that almost everyone has, even to this day, what we call sanity, is actually false. The true way the universe works for electrons, protons, and neutrons, which make everything up in our world, including us, the true way would be more consistent with like the magic of a Harry Potter movie, or possibly what the views that people hold that are clinically insane. So that's why Niels Bohr said, if quantum physics hasn't profoundly shocked you, then you haven't understood it yet. But maybe he could have said this. He could have said, if quantum physics hasn't profoundly shocked you yet, then maybe you need a better teacher. Because if you weren't shocked, then I did a bad job. I didn't really show you the true nature of what the theory was saying. But the question is this theory true? Well, today we're going to learn about an experiment that's probably the most dramatic, the most conclusive evidence that the theory is in fact true. So what I have here are 3 glass tubes, and I'm going to pass some current through them with some high voltage power supplies. So as you can see, they glow different colors. In this glass tube, there's hydrogen gas. In this glass tube, there's mercury in a vapor form. And in this glass tube, there's the element of neon. And what you could see is that all the elements give off different colors. But in fact, it may look like they're giving off one color, but actually each of these is multiple colors shining at the same time, blending to give us that perception. So what we could do is we could use this device, a spectrometer, which is difficult to see in the low light. And what it does is it separates the colors that come off of these glass tubes into all their component colors. And what we're going to do is we're going to use that device now to take a look at all the colors that come from these tubes. So let's have a look. So what I have here is one of these spectrometers clamped in this ring stand with a camera looking into it. So when I switch to this camera view, it's going to be what you would see if you were here doing an experiment looking into the end of it like this. I'm going to send light in here, and then what a spectrometer does is it separates a single light beam into all the colors that make up that light beam. So first, what I'm going to do is I'm going to take this white light here and I'm going to put it over here, and you'll see what happens to that white light when it goes through the spectrometer. So let me change the view. Now, as you can see, I haven't put the white light in yet. There's a scale on the bottom that measures the wavelength of the light in nanometers. Note that the scale goes backwards. Usually number scales go from left to right. This one goes from right to left. It starts at 400 on the right side and ends at 700 on the left side. So you have to kind of count the opposite way you're used to. Now here comes the white light. And as you can see, it creates a rainbow. So this splits, again, all the colors of the white light into all its colors. And you could see that the red light reaches almost 700 nanometers, and then the violet light reaches nearly 400 nanometers on the right side of the scale. So that's the spectrometer with white light. The next thing that I'm going to do is I'm going to take a light that came out of the hydrogen atom, the excited hydrogen atoms in this glass tube. I'll turn this on. You see that this looks right here like a purplish, reddish, purple color of light coming out of here, but we'll see from the spectrometer that, as I said, it's a mixture of colors. So let's have a look. Now, as you can see, there's primarily three bright lines. There's a red one somewhere at 650 nanometers. I'm having a little trouble with the focus here. Yeah, 650 nanometers, and that's on the left side. Then there's like a bluish, greenish line right to the right of 500, so that'd be like about 480 maybe. And then there's a violet line at approximately 430 nanometers on the right side of the scale. So that is the spectrum of hydrogen light. if I do this again and again, day in and day out on different parts of the world, different planets, the hydrogen always makes those kind of lines in the same exact place. Now what I'm going to do is I'm going to switch this glass tube and show you Mercury spectrum. So I have to take this out carefully because it gets kind of hot. And here you go, right from the start, you could see it's a different color. It's more bluish. It doesn't have that red tint to it. So let's have a look in the spectrometer. All right, this is looking nice. So you see now, this has a different spectrum. All the way on the left, we have a red light, again, at somewhere around 650. And then we've got a few green lines, but there's a dominant one about 540. Focus is going in and out here. And then there's a bluish line and a violet line. So again, this is a color signature that's specific to mercury vapor gas. And then, next what I'm going to do is I'm going to change this out and we'll take a look at helium. I mean, you already get the idea from these two. But you see here again, this is this bright red light. Let's have a look in the spectrometer. All right, so here you go. You could see that there's a lot of red lines, green lines, violet. This one has a lot of colors, a lot of different bands. Again, this is the signature of the neon light. Now, as I already said, every element on the periodic table has its own pattern. Like here's an image that shows you a few different spectrums for different elements. You see all of them are different. In fact, you can use this just like you use a fingerprint to solve a crime. If you have a sample of something and you don't know what it is, you could use the spectrum to identify it. Look at this image at the top. The top shows that the, the sample is unknown. But if you look at the sample, other samples there, known samples, you see the fifth one down matches the spectrum of the unknown. So we would be able to identify that as strontium. One final point, the emission spectrum. It's when the gas is excited. You could heat it up, you could pass electricity, and then it'll release the lights that we saw in the spectrometer. But if you took white light, as you see in this image, and you shine the white light into or through the cool gas, what would happen is it would subtract out the same colors that are emitted when the gas is hot. So whether the gas is emitting the light or absorbing it, it's always absorbing exactly the same colors, the ones that we saw in the spectrometer. Now before we go on, let's take some notes summarizing what we've seen so far. So I decided to go with paper notes for this bit of notes because it allows me to use these markers nicely to kind of simulate the spectrum. So today's topic, Modern 3, the Bohr Model. And so the first thing I drew out was the case of an emission spectrum. As we saw, we had an excited gas. I excited with electricity, but you could also make it hot. The light that came out when I passed it through the spectrometer produced this certain pattern here, specific colors or frequencies that were like a fingerprint that we could use even to identify an unknown substance. The other possibility is an absorption spectrum, as we saw in the image I had up just a second ago. We take white light, which is all the colors here would be a full rainbow, but when it passes through this non-excited gas, it subtracts these same colors. So now the full rainbow coming out of the spectrometer is missing these same exact colors. So I didn't want to draw it because it'd be awkward with a marker, but basically full rainbow minus the same colors as above. So go ahead, take a moment, and copy those notes down. Now, of course, the question is, why do atoms do this? But before I answer that question, first, I want to remind you that when we're talking about certain colors of light, what we're really talking about are certain frequencies and therefore certain wavelengths of light. And if you recall, we learned in the first video on this topic that light is actually made of tiny little submicroscopic bullets called photons. Each of those little bullets has a certain amount of energy. E equals hf, or hc over lambda. So when we say an atom only absorbs certain colors or emits certain colors, what we're really saying is it only absorbs certain exact energies and only releases certain exact energies. And how would it absorb and release energies in the first place? Well, remember, an atom is protons in the middle and electrons orbiting around. Kind of similar to like maybe if you had planet Earth and you put a satellite in orbit and it's going around. Now, if you wanted that satellite to go to a higher orbit, what you would need is rocket thrusters to add energy so it would start increasing its altitude. If it were losing energy, it would be spiraling toward the planet and maybe even crash into the planet. And when it comes to satellites, they can go gradually to any orbit radius and therefore orbit energy that you want. You could put the rocket thruster on for a little blip, maybe a second or two, and go up like maybe a millimeter in orbit, increase the energy just a little bit. But yet, when it came to electrons, they're orbiting here, and then they can't just absorb a little bit of energy, as we saw. They have to absorb only certain colors, certain energies, and pop up to some higher orbit. Pop up to another one. They can only absorb fixed jumps of energy, and they can only release fixed jumps of energy. And why would that happen? When you're thinking about the Earth and the satellite, it's unfathomable. You could put the satellite anywhere you want. But that's because you're thinking of the satellite as a solid particle. Kind of like we were just thinking of the electron as a solid particle orbiting the nucleus of an atom. But it isn't. What would happen if instead we imagine not the electron orbiting as a particle, but one of those waves we talked about, those imaginary waves that, we get from Schrodinger's equations. So if we think that way, let's see if that comes up or explains away this behavior of atoms. So here we are. What we're going to be talking about is the Bohr model, finally, the orbit diagram for hydrogen. And the simplest case we could have when we envision a wave orbiting around the proton of a hydrogen atom, the nucleus of a hydrogen atom, is the case when we have exactly one wavelength wrap around the proton or the nucleus. And so you see here this little C, that represents the crest of a wave. Halfway around, we reach a trough. That's what follows a crest. And then when the wave comes around again, crest meets crest, and that's what we call constructive interference from waves. And that means the wave tends to reinforce itself when crests always meet crests and troughs always meet troughs. That's constructive interference. That's the simplest case. We call that the ground state, and we give it a number, n equals 1, and that means the circumference exactly matches one wavelength. Now let's suppose we try and boost that electron up to a higher orbit. Like in the case of gravity, we'd fire some rocket thrusters. Well, in this case, we can bombard this gas with some electricity, as we saw, or we could even heat it up. So we try to bump this electron up to a slightly higher level. Now, what happens then is as the wave wraps around, we have a crest followed by a trough, followed by a crest, and then what follows a crest is a trough, and then a crest. And you see that every time this wave goes around, the trough is meeting the crest, and the crest is meeting a trough. That is destructive interference. In other words, the wave cancels. So the electron's wave cancels, or I should say the electron as a wave cancels in this location. And as you remember from the last video, when there's no amplitude to a wave, that means the probability of finding the particle in this region is 0 because the amplitude is 0, because the wave's canceled, which is another way to say the probability of being somewhere is 0. That means it can never be there. The electron can never go to this energy. So that energy I tried to add will not be absorbed. But if I give it even more energy, it'll go to possibly even a higher orbit, which I have drawn here. Now, as the wave wraps around, crest follows trough, trough follows crest, then another crest, trough, and then on the second pass, crest again, meeting crest. After a crest, a trough, meeting trough. So crests always meet and troughs always meet. That again is constructive interference, which means the wave reinforces itself here, which means there's a high probability of finding the particle there. So the electron can jump to this second orbit, skip over this to this, and that's when two waves fit in the circumference, and we label that the n equals 2 orbit. Let's suppose hypothetically I try and, in this state, add even more energy. And now, so I bump this electron or try and bump it a little higher. What happens in this case, crest, trough, crest, trough, crest, trough, crest and trough are meeting, then trough followed by crest, trough and crest are meeting. This is again destructive interference. The wave cancels here, the electron can never be here. So if I add even more energy, not this amount, but this amount, we see again, 3 wavelengths will fit in the circumference. Crest, trough, crest, there's one. Trough, crest, another. Trough, crest, 3 waves. And then after trough, I've got a crest, trough, crest, and crests and troughs are meeting. That's again constructive interference. That's the n equals 3, where 3 waves fit in the orbit. And then one more example, the fourth n, where 4 waves fit. And again, trough followed by crest, followed by trough. They reinforce, so that's the n equals 4. So this finally explains why atoms can absorb only fixed amounts of energy, and when they go back down, they could only emit fixed amounts of energy as they go from orbit to orbit to orbit, skipping all these other orbits. So it finally explained that away. Tremendous achievement of the conceptualizing an electron as a wave, not as a particle. Then finally, the experiments are explained. So let me create a pause to give you a chance to copy these notes down. Now you could calculate what these energies are. In fact, if you take college physics, maybe in your second semester, or maybe even your third semester, you might have to calculate these. And it's possible with, you could use the de Broglie wavelength, and you could use, hold on, lights are out, and you can use certain orbit relationships, but you don't have to derive those energies yourself, because on the reference table, the energies are here listed for you for 2 atoms, hydrogen and mercury. Now the first thing, note that the top of these energy level diagrams are 0. That represents the case when the electron is completely out of the atom. But then when it falls back into orbit, it falls and gets a lesser energy. When something falls down, it goes to a lower energy. So as it's going to lower orbits, it goes decreasing from 0. That means the energies are all negative. Every energy level diagram for all atoms, the energies are all negative for all these particular orbits. And it kind of flips things around a little bit and might be confusing at first. For example, if I told you something, a hydrogen atom went from the n equals 1 to the n equals 2, the energies that correspond to these orbits in electron volts are negative 13.6 here, and then when it jumps to this orbit, it goes to negative 3.4. You might think that looks like a decrease in energy. It is not. Negative 13.6 to negative 3.4 is an increase in energy. Think about being $13 in debt and then only $3 in debt. You gain $10, right? So it kind of looks backwards as the numbers look like they're getting smaller, they're actually getting bigger. And then, of course, when the atom electron jumps back down, it goes more negative, so the energy in the atom decreases, energy increases. So these are the energies. You'll always have your reference table with you, and so you don't have to write them down. But what I want to do is I'm going to copy the energies of the hydrogen because there's a lot of concepts, quantum physics concepts, that we have to know about these energy level diagrams. So here we are. the Bohr model energy level diagram. So you're going to sketch this energy levels here. Just do your best to draw the n equals 1, 2, 3, 4. Notice the numbers, and then the energies in electron volts. 0 at the top, most negative here, what we call the ground state down here. So now imagine all these different scenarios over here. In case A, what happens is we've got a photon coming in when the hydrogen atom is in the ground state here. In other words, the electron is not excited, it's at the bottom orbit, and it has 10.19 EVs. If you subtracted these two numbers, you would see that it's 10.2 EVs from here to here. And so, obviously, it's not enough to reach the n equals 2. Most people would say, okay, you don't have enough, then you're not going to go up to this level, you're going to stay here, and that energy just passes through the atom, it doesn't get absorbed, and the electron stays in the n equals 1. In case B, now energy comes in, maybe it's a photon or thermal energy of 10.2 EVs. That's the exact difference between these two numbers if you subtracted them, 10.2 to rise to here. That's enough to get to the n equals 2, so the atom now absorbs the energy and the electron rises from n equals 1 to n equals 2. So now the orbit goes pop to the second orbit, and the electron is here in this energy level diagram, having absorbed this much energy. Now let's suppose a third scenario. Remember, 10.2 from here to here. And then energy comes in at 10.21 EVs, a little bit beyond the n equals 2. Now most people would say, yeah, that's enough energy to get into the n equals 2, so it should rise to the n equals 2. Not the case. The atom absorbs no energy because it's not exactly the amount of energy to get to n equals 2. So it doesn't work like money. Like, for example, if you went to the movie theater and it was $10.20 to get into the movies, and you showed up with $10.21 in your pocket, the movie teller would not say, sorry, you have too much money, you can't go watch the movies, right? You'd go in, they'd give you change or whatever. But with atoms, it doesn't work that way. The energy has to be exact. Any more, and it's not going to absorb it. Okay, so kind of unusual. The fourth scenario, D, what if energy comes in this increment? Maybe it's a photon, maybe it's electrical energy or something. So notice 12.09 is the energy difference between these two if you subtracted these two numbers. That's enough to jump and skip the n equals 2 and go straight from 1 to 3. So you can skip energy levels on the way up or way down. It's fine. So that's possible. Another scenario, let's suppose there are 2 bits of energy, 2 photons maybe. One hits with 10.2, and then the next one hits with 1.89. That's also allowed because the 10.2 is exactly the amount to get to the second level, and then the 1.89 is the exact difference from here, enough to get to the third level. Okay, so that's another scenario. Now, if you get 12, so notice these are together add up to 12.09. If you get 12 and then 0.09, it's not going to move anywhere. The electron will still stay in the n equals 1. You always have to only absorb to some exact energy level at all times for all transitions. Even though these two combine to get enough here, it's not in the right pattern. So the electron stays in the ground state. Final point, any energy above 13.6 gets us out of the atom, and then it's allowed. You could get 13.6, 13.61, 13.62. As long as you go beyond here, when the electron is free of the atom, you can absorb any amount of energy, and then the extra energy is kinetic energy. So a lot of concepts here. Let me create a pause so you could copy all these notes down. All right, now what I'm going to do is three examples calculating the energy of photons using these energy level diagrams, but I think it'll be better if I switch to the chalkboard. So here's our first example. An electron is in n initial equals 5, goes to n final equals 2, A, is the photon released or absorbed? B, determine the energy in joules. C, determine the frequency. D, determine the photon type. So first thing, right off the bat, we could tell this is a hydrogen atom. If it were a mercury atom, the states would be labeled in letters instead of numbers. So in part A, is the photon released or absorbed? So first thing, we see that n equals 5 is way up here, and then it goes down to the n equals 2. So since the electron's dropping down, it means the photon is released, because energy has to be released for the electron to drop. So we could answer released. B, determine the energy in joules. So we have these energy levels in the reference table. In order to find the energy that's released, we have to find the energy difference between those two states. And so I recommend writing the formula like this. It's written differently on the reference table, but I always put absolute values because the photon energy is never negative. It's either a photon coming out of the atom or going in, but it always has positive energy, whether it's independent of what direction it's going in. So if you don't put these absolute values, sometimes you get a minus sign in your answer, and then you report the energy and frequency negative, and you get points off. So we look up, actually, you know what I should do? Maybe I'll go final minus the initial. I guess, no, you know what? Maybe I'll stick with 5 and final and initial. Clear. All right, so we go to our reference table to find what those energies are, and you can see that the n equals 5 is right here, negative 0.54, and the n equals 2 is negative 3.4. So those are the two energies in EVs. So I'll just continue on this line, absolute value. The final, as I said, was negative 3.4. Also, caution, don't forget the EVs. A lot of students do on these problems. Minus the initial energy, which was the 5 of negative 0.54. And see, if I didn't put the absolute values here, I would get a negative, because this is negative, negative plus. So I'm taking negative 3.4 and adding 0.54, and that gives me 2.86 electron volts. But not the answer. They want the energy in joules. So as we learned in the photon video, we have to do a conversion like chemistry dimensional analysis. So we want the EVs to go away, so we're going to put EVs on the bottom and joules on the top. Now, what's the conversion? What numbers go here? You go to the front cover of the reference table. Maybe I'll not go again, but basically right around here, you have 1 electron volt is 1.6 times 10 minus 19 joules. So you got to put 1 electron volt, 1.6 times 10 to the minus 19th goes with the joules. The EVs go away, and it leaves me with joules, so I'm just multiplying that by that and dividing by 1, which gives me 4.58 times 10 to the minus 19th. There's my answer. The next thing, C, determine the frequency. So we look up the formula that relates energy and frequency, and that's again in the modern physics section here. This is new, so I'll show you here. E photon is either HF or HC over lambda. They ask for the frequency, so we're going to use E equals HF. There's the energy. Planck's constant you get from the front cover of the reference table. Maybe I won't come up again, but basically it's right here in the front cover where my index finger is. Planck's constant 6.63. And don't forget the units. A lot of times students put joule per second. I don't know why, but don't do joule per second. It's a joule times a second, so make sure you don't do that. All right, so what we're going to do is divide by Planck's constant and be careful with the exponent. And what we get there is 6.9 times 10 to the 14th. So there's the frequency. And then the last question D, determine the photon type. This is pretty popular on the Regents, is when you get the frequency in these problems to go back and report what kind of light that is. So we go to our electromagnetic spectrum. So 10 to the 14th hertz, first of all, it's somewhere in the visible light here, because if it were like, say, 10 to the 15th or 16th, it could be ultraviolet, or if it were, up here, it could be X-ray or gamma ray. But it's within this range. 6.9 is between 6.59 and 7.69, so it's in between these two frequencies. In other words, it's violet light. So that's the answer to D. Let me create a pause to give you a chance to copy these notes down. Let's do a second example. Okay, so an electron in Mercury's C state absorbs a photon with a certain wavelength. Determine the energy of the photon in EVs, that's part A, and determine the final state of the Mercury atom. So the first thing, part A, we need to find the energy from a wavelength. And HC over lambda doesn't work in this case. I mean, HF doesn't work because we don't have the frequency. So we would use HC over lambda. And then H is Planck's constant, front cover of the reference table. C, front cover of the reference table, speed of light in a vacuum. So we plug that in, 3 times 10 to the 8th. Can't forget the units. And then that's all over the wavelength, 6.87. So then I punch that on a calculator, and what I get is 2.90 times 10 to the minus 19th. Problem is that's in joules, and they wanted the energy in electron volts. So once again, we've got to do like a chemistry dimensional analysis. So we take that energy, we multiply by a fraction. Again, don't put an equal sign here. We want the joules to go away, so I'm going to put the joules in the bottom here, and we want to be left with EVs, so I put the EVs in the top. So now we need to know what numbers to put here. What goes with the joules, what goes with the EVs? We go to the front cover of the reference table. Again, I won't come to the screen again because that will, it's too much, making you dizzy maybe. So right about here you see 1 electron volt is 1.6 times 10 minus 19 joules. You could look it up on your own reference table if you want. So 1 electron volt, 1.6 times 10 to the minus 19th joules. The joules goes away, leaving us just the electron volts. So what that comes out to be is you take this, you multiply by 1, and then you divide by this 1.6 times 10 to the minus 19th very carefully, and you get energy of 1.81. The next part. So what energy do we end up in? So in this case, the problem said that the Mercury was in the C state over here, the electron. So since it's absorbing a photon, it's going to go some higher level here. It's not going to go down. That's when it releases a photon. When it absorbs, it goes up. So what we are in is this energy, negative 5.52, and then we absorb 1.81. So we're going to add that up to see how high it goes to what level. So we could write that as a formula that the energy final is the energy initial plus the energy of the photon, because it's going to make it bump up when it gets absorbed. So as I said, energy initial in the C state was 5.52 EVs, and then the photon energy was negative. The photon energy was 1.81. And so when you punch that on a calculator, you get negative 3.71. Well, that's not the answer because they asked the final state, not the final energy. So what we have to do now is look at the energy level diagram and see. So it started here, and then it jumped to negative 3.71, which is right here, which is the E state. So that's the answer. It went into the E state. So let me create a pause to give you a chance to copy these notes down. All right, another example. This one's a little bit shorter, so Okay, so now we get this much energy. We're in the C state, which as we saw is this. Notice that we get more than enough to go beyond zero. To get to zero is the bare minimum to break free of the atom. So if you get more than the energy you currently have of the state, then the electron flies away from the atom and the excess energy remains kinetic energy. So you could simply find the energy final like we did over there. It'll be energy initial plus energy photon. And so that's the C state energy we get off the reference table. The photon came in with, and when you punch that on the calculator, you get kinetic energy is the final energy. Now it's kinetic energy of 1.71 EVs. If you wanted to, you could take this and convert it to joules, as we did with that, chemistry dimensional analysis, and then you could plug that into Ke equals 1/2 mv squared. Look up the mass of the electron, and you could solve for how fast that electron flies away from that mercury atom once it's been liberated. So let me create a pause to give you a chance to copy these notes down. So that was the Bohr model of the atom. Again, to recap, if you accept that the electron is not a particle, but a wave that wraps around the nucleus of an atom, then you can understand and explain why atoms absorb energy in fixed steps and why they release energy in those same fixed steps. And that was a tremendous achievement for quantum physics. And because it explained so much of that experiment, that phenomenon, it was regarded as true. But quantum physics did so much more for our understanding. If you solve Schrodinger's equation, which I wrote on the board in our last video, for the wave function, and by the way, humans can, even the smartest human can only solve for this wave function for the simplest element, hydrogen. So if you wanted to find what the wave function was for more complicated elements like even helium, neon, chlorine, you need a computer. So the computer takes this equation, churns out a wave function. If you took that same computer and you plotted the wave functions, you would see images like this. Now you probably recognize these from chemistry class. These are the S, P, D, and F orbitals that are encoded in the periodic table. And basically, those, if you think about it, were pretty much the heart of chemistry. They gave us things like the octet rule, allowed us to understand why hydrogen and oxygen combine as H2O, or carbon and oxygen, CO2, sodium and chlorine, NaCl, or why carbon can form long chains like in protein molecules in our muscles, or in fat cells where we store energy, or in long chains like in our DNA. So those orbitals, key to understanding genetics even, life itself. And in other practical instances, those orbitals allow us to understand things like why silicon is a semiconductor, why we can use it in computer chips. And because people understand the true nature of an electron as it's zipping around atoms, they can build computer chips faster, faster, faster that do all the things, your cell phones, computers that analyze things. All these things, they come from Schrodinger's equation, from accepting that an electron or any subatomic particle is not a particle. It's not a real thing. It is literally imaginary. It's a wave that moves through the world. And that means these particles, like electrons, can go through walls. They can be in multiple places at one time. They can pass through other electrons. They can be nowhere at all. And they can pop in and out of existence, especially when they pop in and out of particle existence, especially when there's an observer. I turn my back on an electron, it's a wave. I turn and I observe it, and it seems As far as we could tell, the wave imaginary function disappears, and in its place a particle appears in a random location somewhere where the amplitude is not zero. All that crazy stuff, that insane stuff that was so hard to believe, it's at the heart of all of our knowledge: computers, DNA, chemistry, quantum physics, okay? So, it really is true, all that remarkable stuff. So that's what we saw today in the Bohr model. I hope you enjoyed the physics. I hope you found it even a quarter or a tenth as fascinating as I do. Then you would have really enjoyed the physics. I'll see you in the next physics video.